In our last two lectures, we talked through rigorous coupled wave analysis. There are a whole bunch of miscellaneous topics that I want to go through that I lumped into this lecture 21, rigorous coupled wave analysis tips and tricks. First, I want to talk a little bit about what it means to retain only one spatial harmonic. There are some interesting things we can do and some interesting insights in that. Next, I want to move on to using a fully three-dimensional rigorous coupled wave analysis tool to model a 1D grating, which is a rather simple case, but we can do it pretty efficiently still with a three-dimensional rigorous coupled wave analysis, and we'll borrow from our discussion of this one spatial harmonic thing. And this is almost to the point where it's not worth developing a two-dimensional RCWA for modeling 1D gratings because the 3D is so fast and efficient. However, if we're lumping our model into an optimization that iterates a million times, maybe then it makes some sense to develop a two-dimensional RCWA, which is our next topic. And it's easy to incorporate fast Fourier factorization for a two-dimensional RCWA. It's not so straightforward for 3 dimensions. So I'll step you through that formulation with fast Fourier factorization. The next thing is a danger in RCWA. Conservation of energy is very good no matter how many spatial harmonics we use. In real space methods, if we limit the number of points in the grid, there's some real obvious signs that things are going wrong. RCWA does not have those signs, so having a habit of always checking for convergence is very, very important here. Next, I want to talk about rigorous coupled wave analysis and curve structures and what that looks like and a staircase approximation. And then second to last topic is strategically truncating the spatial harmonics. Which spatial harmonics we retain is completely arbitrary, and in fact we're free to even choose what direction those spatial harmonics are. It's most efficient to choose the directions of the spatial harmonics to be consistent with diffraction theory, but it's not necessary. We can choose other directions. We'll stick with the directions that come out of diffraction theory, but our choice, there's more to that, and I want to talk you through that. And then the last thing, it's also possible to model a hexagonal grating with a rectangular rigorous coupled wave analysis with a couple tricks. We can generalize RCWA, and we alluded to that in some earlier lectures about how that would be done. But rather than reformulate and rewrite a whole code, it turns out we can still do that with a rectangular rigorous coupled wave analysis with a small hit in efficiency, but we can still do that. On to the deal of one spatial harmonic and what that means. First, we want to take a look at the convolution matrix again. So at the upper left, we have a unit cell. It's some kind of dielectric with an air hole. So remember, in the direction coming in and out of the screen here, that's infinitely extruded. When we look at the cross section, we construct a convolution matrix, and I'm showing that on the right. Now, going down the center diagonal, it turns out is the average value in that function to the upper left. So we have a bunch of 1s here, a bunch of 9s out here. If we average this value, it comes out being almost 6. So these numbers going down the center diagonal is the average value. And it also corresponds to the 0 order harmonic. Now as we go off the diagonal, these are the higher order Fourier coefficients. And so the more modulation there is in the dielectric function, the more numbers we expect to see off of the diagonal. But the important thing is that center diagonal is the 0 order Fourier coefficient and is the mean value of the dielectric function. So what happens if we run our rigorous coupled wave analysis code, but we use only one spatial harmonic? So capital P and capital Q are both 1. What does that mean? Well, remember from the last slide that 0 order spatial harmonic is the mean average value. So if we look at our layers here, this has some modulation in it. There's probably a bit more complicated diffraction happening here. But our convolution matrix, if we're only retaining one spatial harmonic, has calculated an average value in each of these layers. So in fact, what we're simulating looks like a stack of homogeneous slabs. And in fact, rigorous coupled wave analysis defaults back to the transfer matrix method. The only difference is we're able to input to it arbitrary structures in the cross-section that are gratings and other things, but it averages that out. And so we're really running a transfer matrix method simulation with average material properties in each layer. And in fact, there's a whole bunch of papers that approach effective medium theory from this perspective. They developed this Fourier space mathematical formalism. They only retain one, sometimes two, spatial harmonics, and they derive effective material properties from that. So when we use only one spatial harmonic, this really means we're just going with the average value. On to simulating 1D gratings with a fully 3D rigorous coupled wave analysis. First, we need some terminology. We have what we call a one-dimensional grating, meaning there's really only periodicity. There's only a change in the dielectric function along one axis. So we would call this a 1D grating. However, to model a 1D grating, we need a 2D simulation. Then we have what we call a crossed grating, or a 2D grating, but to model this requires a 3D simulation. So don't get tripped up in the words here. A 1D grating requires a 2D simulation. A 2D grating requires a 3D simulation. So from previous lectures, it's no surprise to us if we have a one-dimensional grating, that is a two-dimensional device, that Maxwell's equations break up into two distinct modes. Now, if we are running a fully three-dimensional rigorous coupled wave analysis, we certainly have these electromagnetic modes. However, we're calculating them both at the same time. So if we're only interested in one of those modes, well, we're calculating the other one anyway, and that is perhaps some inefficiency. In addition, it's actually quicker to model both separately rather than both at the same time because it involves smaller matrices. But it certainly can do it. When we simulate a 1D grating with 3D rigorous coupled wave analysis, we're really modeling both polarizations, both modes at the same time. But rigorous coupled wave analysis is a very fast, very efficient method for structures that have low to moderate index contrast. And I am not sure it's really worth your time to develop a separate two-dimensional RCWA. It certainly would if it's something you're going to iterate hundreds of thousands or millions of times. But otherwise, I would develop just a single three-dimensional RCWA, which is what we're doing for this class, and running 1D simulations with it. So let's talk a bit more about how that can be done. So here's a one-dimensional grating, and we will model this with our three-dimensional code. So notice in this direction we see the grating. So our dielectric constant is changing in this almost horizontal direction. So in this direction, if this is the P direction, we will need some number of spatial harmonics, maybe 11 or 21 or something like that. Now we have this other direction. There is no change in the dielectric constant in this direction. There's no modulation, really nothing interesting happening in this direction. It's the extruded direction, if you will. Well, if nothing's changing in this direction, we actually only need one spatial harmonic in that direction. And in fact, that is how we take our three-dimensional rigorous coupled wave analysis and as efficiently as we can model a one-dimensional structure. We look at that extruded direction and we only use one spatial harmonic in that direction. Now in the other direction it follows the same rules, and we need 7 to 10 spatial harmonics per every wavelength wide that the period is. So now we're experts on using a three-dimensional rigorous coupled wave analysis for one-dimensional gratings, but maybe we want to iterate this a million times. We want that extra efficiency. How do we formulate a two-dimensional rigorous coupled wave analysis? And it turns out, if you remember, we talked about fast Fourier factorization when we were discussing Maxwell's equations in Fourier space. It's very straightforward to incorporate that into 2D RCWA. Not so straightforward for a three-dimensional rigorous coupled wave analysis, so we really didn't discuss that. So we start here. This is the matrix form of Maxwell's equations. They're also in Fourier space. We started the three-dimensional rigorous coupled wave analysis formulation here. So we start at the same point. But now we're going to reduce the dimensionality. We'll let the extruded direction be the y direction. Well, if that's the extruded direction and we restrict the waves to be in the xz plane, then there's no components to the wave vectors in the y direction. They all have to be 0. So that's when the device is infinitely extruded in the y direction and we restrict wave propagation to be in the xz plane. So those are the two conditions that we can set all y components of the wave vectors for all the spatial harmonics to 0. When we do that, Maxwell's equations now look like this. There's a few terms here that have dropped out, and just like we're used to, these sets of equations will now decouple into two independent modes. So that's what happens here. At the top are our original 6 equations. I've now color-coded them so that the red equations go together and then the blue equations go together. So we have an E and an H mode. That should not be a surprise. And in fact, how we handle these should not be a surprise. We're going to take the second and third equations for each of these modes, substitute for the x and z components, and substitute that back into the original equation, and we'll get a single matrix equation in one variable instead of having 3 now. Before we do that, let's think about how these different components are oriented. So we have S and U. S are the amplitudes of the spatial harmonics for the electric fields, and the U's the amplitudes of the spatial harmonics for the magnetic fields. So let's say we have a 1D grating that looks something like this, and we define our coordinates this way. So Z will be this longitudinal direction, X will be in the direction we have the modulation, and Y will be in this uniform direction. So it's in and out of the screen in this case. Well, Z inside the layer is parallel to all the interfaces. We might think, well, it's perpendicular from this layer to the next, but we're only interested in this field component within the layer. So think about being in the middle. The Z component is parallel to any possible surface we could have. Remember, when we're doing rigorous coupled wave analysis, we're modeling layers that are uniform in this Z direction. So any component in the Z direction has to be parallel to interfaces. Likewise, the Y component. This is always parallel to interfaces. However, the X component is always perpendicular to interfaces. So for a two-dimensional rigorous coupled wave analysis, for modeling one-dimensional gratings, the Z and Y components are always parallel to interfaces. The X component is always perpendicular to interfaces. And this goes for both S and U. And this is critical because this is going to guide us in how we incorporate fast Fourier factorization. So here we go. These are our 3 equations now for the E and H mode. And notice I've done something a little bit crazy. I put these double brackets around these. So what the double brackets mean is that we're surrounding a convolution matrix. And notice we're doing this weird double reciprocal thing here, and that shouldn't be a surprise from our discussion of fast Fourier factorization. But let's think about this. So for the E mode, from our last slide, the Y component of S is always parallel to interfaces. And if you remember from our fast Fourier factorization discussion, we don't do anything other than construct the ordinary convolution matrix. UZ is also always parallel to interfaces, again from our discussion on the previous slide. So this mu sub r with just the double square brackets, that is just the ordinary convolution matrix. Now UX is always perpendicular to the interfaces. So remember what we do here when we have, this is a problem case where we have the product of two functions in Fourier space that produce some convergence issues, and we fix this using fast Fourier factorization rules. So what we'll do is we'll take in this case, the permeability function, mu sub r, and we'll take the reciprocal of that. So now we're working with 1 divided by the permeability function. We'll take that reciprocal function and construct a convolution matrix. Once we have the convolution matrix, we take the reciprocal again. So I like to just call this the double reciprocal thing, but in fact, this is the convolution matrix we use to incorporate fast Fourier factorization for the E mode. Now in the H mode, the UY and the SZ are always parallel to interfaces, so they get standard convolution matrices. It's the SX component that's always perpendicular to interfaces, so this is where we incorporate our fast Fourier factorization rules. We take the reciprocal of the permittivity function, construct a convolution matrix from that, and then invert that convolution matrix. So in principle, we should be back to just the ordinary convolution matrix. So in principle, I guess these two would be the same thing, but if we think about this a little bit more, it turns out these matrices are a little bit different. And that's good, because if they weren't different, we wouldn't be fixing this problem that we have with the product of 2 Fourier series where there's a discontinuity. So for a 2-dimensional rigorous coupled wave analysis, it's very easy to incorporate fast Fourier factorization, and it happens in this step. And you'll notice it happens in basically the same equation. It happens in these 2 middle equations. In the first equation and the third equation, we have the standard convolution matrices. In this second equation, we have the double reciprocal thing. Well, now we just retain these convolution matrices that we have in there, and we proceed just as we would expect. We will solve now the third equation for the Z component, UZ and SZ, and we will substitute those expressions into the remaining 2 equations. So here we are. Here's our remaining 2 equations for the E mode and our remaining 2 equations for the H mode. And notice we've rearranged terms. We brought the derivatives over to the left and all the other terms over to the right. Well, now we can put these 2 equations in our standard PQ form. And for each mode, we have 2 matrix differential equations that we can write as P and Q. And here's P and Q for the E mode. And here's our 2 matrix differential equations for the H mode and our P and Q for the H mode. And so notice the fast Fourier factorization is completely built into just the calculation of P. The calculation of Q uses the standard convolution matrices that we've been discussing. It's the P that's using the double reciprocal thing to calculate the improved, if you will, convolution matrices, or the proper convolution matrices that follow the fast Fourier factorization rules. So here's our matrix wave equations. We will let the matrix omega squared equal P times Q. And now we have our matrix wave equation again. And this looks exactly like what we saw for transfer matrix method. It looks exactly like what we saw for 3-dimensional rigorous coupled wave analysis. And in fact, it's handled the same way. All the equations for scattering matrices, etc., it's all the same. So once we're in this PQ form, the rest of the method looks the same. So let's look at some convergence data from this. And I just did a simple binary grating. And I did 2 cases. One where the outside is air, and we go to a dielectric constant of 3. And then in the second case, we go from air to something with a dielectric constant of 40. And I'm comparing the convergence between the ordinary RCWA, as if we didn't do anything about fast Fourier factorization. And then in blue, we're showing fast Fourier factorization. So what I'm plotting is the overall reflectance as a function of the number of spatial harmonics that we're retaining in the expansion. And what we can see, and maybe I should have zoomed in on this to make it look a little bit clearer, but fast Fourier factorization definitely converges faster. I'm taking it out probably way too many spatial harmonics to make this meaningful, but if we zoomed in right here, you'd be convinced that the fast Fourier factorization for this case converged faster. Now let's look at the case of 40. Well, fast Fourier factorization converged even faster. And we see actually once we get up to a certain number of spatial harmonics, convergence is quite slow for the ordinary. So as we go to higher contrast, fast Fourier factorization is buying us more. So now let's look at something other than a square grating. Let's look at a grating that has circles in it. Now these are curved structures. This is something we're going to talk about later in this lecture, but we essentially have to divide this up in a whole bunch of layers. And I actually forget how many layers I had here, but I'll say 20. And we look at the convergence difference. Again, number of spatial harmonics, and we're looking at what's happening with the overall reflectance. Well, with low dielectric constants, we're going from air to dielectric constant of 3, we see fast Fourier factorization converges faster, no issues. Well, what if we go to high permittivity, something with a dielectric constant of 40, and we look at the two? Here it actually looks like the ordinary is converging faster. So my conclusion here is I think the jury is still out on under what configurations fast Fourier factorization buys you faster convergence. Certainly for binary gratings and almost all cases, it does buy you a lot of, you can get away with much fewer spatial harmonics. However, in this one case, it seems to be actually hurting. Okay, a danger with rigorous coupled wave analysis, and I didn't initially have this in there, but when I taught this course before, I saw a lot of students falling into a certain number of pitfalls. The last method we developed was finite difference frequency domain, and when we used too few points on the grid, we used too poor grid resolution, there were some telltale signs. We would see a rolling behavior very often in our spectral responses. The conservation of energy was off, and the fields tend to look blocky, and there were all these signs that something's wrong. Well, with rigorous coupled wave analysis, we get great looking answers even with very few spatial harmonics. So in other words, there's really no signs that anything's wrong. We will get a perfectly correct looking answer even if we only use one spatial harmonic. Now it won't be correct, but there's no other signs to tell us that it's not correct. Conservation of energy will be darn near perfect, and there's really no other signs. There'll be no rolling response in the spectral response because there's no reflections from a PML that would cause any kind of standing wave. So this is a danger that it lets us or encourages us to be lazy. And the way around this is we absolutely must look for convergence. So we turn up the number of spatial harmonics, we see how much our answer changes. At some point, there's a diminishing point of return where we increase the number of spatial harmonics, our answer is no longer changing that much. That's convergence. That's what we need to do every time in order to know that we're getting a reasonably accurate answer. So here's a typical convergence plot. And here we're modeling some kind of array of triangles, and we're plotting reflectance as the number of spatial harmonics is increased. So we get this anomalous spike, but for the most part, our answers are jumping around until finally they seem to settle out somewhere around 250 spatial harmonics. And by the way, 250 spatial harmonics is really 15 by 15 harmonics, but ends up being 250 total. But even when we were getting away with just one spatial harmonic here, conservation of energy was good. There's no rolling behavior in the spectral response because remember, this defaults down to transfer matrix method where we've essentially averaged the material properties in each layer through like an effective medium theory. So the answers look good. We absolutely have to look for convergence to know that we're getting a realistic answer. On to curved structures and how to do this. So here's a picture of a very complex photonic crystal, and it looks like a slab consisting of about 10 unit cells. Within each unit cell, it is still curved. So if we divide this up into, say, 20 layers, and we make a staircase approximation, what we're actually modeling looks much more like what's on the right. But if our layers that we've chosen over here are thin enough, well, the staircase approximation is really not that significant. We want to get away with as few layers as possible, but still get an accurate answer. So how do we determine how many layers? We look for convergence. Maybe we set a parameter up top that controls that. In this case, it's 20 layers. We'd set that parameter to 20. Then we'd set it to 10. Does our answer change much? If not, maybe we can get away with 10. But you do another convergence study with the number of layers that you're dividing up to resolve your curves. Now, there are some papers out there, especially when you're modeling metals, that argue for certain polarizations, the staircase approximation never does converge. I've never had that problem, and for the most part, if I'm using rigorous coupled wave analysis, I'm modeling dielectrics where that's really not an issue. But I will warn you that if you model metals, there are those that argue out there that it never does converge to the correct answer, no matter how many layers you use. On to kind of a confusing topic. It has to do with truncating the number of spatial harmonics. The fewer spatial harmonics we use, the faster our codes will run. However, we get poorer accuracy. And so the idea is maybe we can strategically choose which spatial harmonics we leave in the expansion, which we don't, in a way that still buys us efficiency, but we're also can maintain some semblance of accuracy. So some notes here. The choice of which spatial harmonics we retain in our expansion is completely arbitrary. We may not get an accurate answer, but at least in terms of how the algorithm works and not crashing on us, we're free to choose whichever we want. So if we choose them wrong, we get slow convergence, inaccurate results, but it'll still work. The program will not crash. We tend, and almost always, I've never seen it implemented otherwise, although we could, we choose the directions of these spatial harmonics to be consistent with the physics. So we went to diffraction theory, we looked at diffraction through periodic structures, and we can calculate the angles of those. We made our spatial harmonics consistent with that because experience has shown us that's the best thing to do. But it's not necessary. We could do it otherwise, and the code will not crash, and it will still work. Again, it may give us very slow convergence and inaccurate answers, but we are free to do it. The next note is the number of spatial harmonics that we retain in a particular direction tell us the resolution of features we can resolve in that direction. So for example, if in the x direction we set the number of spatial harmonics to 101, we're going to be able to resolve some pretty abrupt changes in the field, some pretty fine physical features in our device in that direction. If in the other direction we only chose 3, it will essentially blur our device in that direction. We're not going to be able to resolve very abruptly changing fields or very fine features in that direction. So if we retain the same number in x and y, well, it turns out we're actually retaining effectively more spatial harmonics along a diagonal, along the 45-degree angle between P and Q. So this means we have better resolution in some directions than others. And a change only as strong as its weakest link. Why are we doing that? So we can actually strategically drop spatial harmonics with some intelligence behind that. So, and the last thing I'll leave you on this slide is that it seems like it's common sense to keep the same number of spatial harmonics in all directions. If we have one direction that only has 3 harmonics, another one that has 100, unless we know something special about our device that maybe it's not changing abruptly in one direction, but it is in another. But typically that's not the case. It wouldn't make sense to do that. We want roughly the same number of harmonics in each direction. So here's what our spatial harmonics look like as we've done it on a rectangular grid. We draw these as not overlapping, although we know that these are overlapping. These are plane waves of infinite extent, and we also know these higher order ones really are evanescent fields and not plane waves at all. But we really have a rectangular grid of these, and if we were looking straight down, we might look at it like this. So our Fourier space grid looks like this, and in this case it looks like we have 19 by 19 spatial harmonics, and we're retaining all of them. But notice now, in the x direction, we have 19 spatial harmonics, and up and down 19 spatial harmonics. But think about the diagonal. in this direction, we actually have more than 19 spatial harmonics. It's 19 times the square root of 2 or something like that. So we actually have better resolution along the diagonal. But is that really buying us anything if we don't have the resolution along the vertical or horizontal axes? I would argue no, and I would argue the spatial harmonics off in these corners are a little bit of a waste. And in fact, we could drop them without reducing our accuracy really at all. So let's look at some different truncation schemes. The simplest is what we've been doing, where we truncate our spatial harmonics to a rectangle, but this is not the only one. So let's think about M and N being the spatial harmonic number, big M and big N being essentially the number of spatial harmonics, and this really is the equation of some kind of crazy circle looking thing. And we have this generic parameter gamma. Well, if gamma is equal to 1, it turns out this is exactly the equation of a circle, and we retain the spatial harmonics in this circle region. This really is dropping the spatial harmonics along the diagonals. Since this is a circle, we are retaining the same number of spatial harmonics in each direction. So common sense tells us that circular truncation is probably the best. Now maybe you have some a priori knowledge about which of the spatial harmonics really have energy in them, and we can choose this arbitrarily. This equation gives us some flexibility. We can look at pincushion type of things where really this boundary here is curved inward, and here we have better resolution along the x and y axes than we have along the diagonal. And if we were choosing this, we probably would want to know that this is actually the case, where the energy's in the spatial harmonics more towards these axes than on the diagonal. Well, we could set gamma to 0.5 and we have diamond truncation. I would argue this really isn't any good, because really all we have is a square truncation again, just rotated with fewer harmonics. So I don't really ever consider diamond. On the other extreme, on the other side of 1, we have barrel truncation. Again, we actually have more resolution along the diagonals than we have along x and y, but still a little bit more efficient. If I use truncation, I tend to use circular truncation, but there may be times where you'd use pincushion or barrel if you have some a priori knowledge about which spatial harmonics have power in them. So one thing you could do is you could solve a problem first with a whole bunch of spatial harmonics on this rectangular grid, and you could plot the power in each of those, and you could see where that power is, and that might help you choose whether you go with pincushion or barrel. And now if you're only changing things slightly in the unit cell, maybe you're running an optimization on it, maybe you can run that a bit quicker now because you have fewer harmonics, smaller matrices, and a faster code. The last topic is modeling a hexagonal grating with a rectangular RCWA. Hexagonal gratings are advantageous from a number of perspectives, but one thing is you can get away with larger feature sizes in a hexagonal array than you could in a square array for operating still at the same frequency or wavelength. And so particularly for optical devices, when you're building things at the micro scale, we tend to like to build larger features because it's hard to make those smaller. So hexagonal arrays are beneficial from that perspective. The radio frequency folks that design frequency selected surfaces will tell you hexagonal arrays, the onset of grating lobes is farther out. What this means is that we can get away with a rather large spacing in a hexagonal array compared to a square array before we start diffracting into higher order modes. So there's some benefits to hexagonal gratings. And from our discussions when we took Maxwell's equations in Fourier space, and we talked a little bit about just using the reciprocal lattice vectors, and we wrote complex Fourier series in terms of those reciprocal lattice vectors, the most efficient code would be formulated that way. But if you've invested all this time and you've developed essentially what I'll call a rectangular rigorous coupled wave analysis, it's still possible to model a hexagonal grating with a little bit of a hit in efficiency. But let's talk about how to do that. First of all, we need some geometry with hexagons. So I'm showing a hexagon here, and at each of the vertices I'm showing a little circle. So if this is a grating, this would be some kind of feature, and we'd have this hexagonal array of these patterns. So in a hexagon, all of our angles are 60 degrees. Each side of the hexagon will be of length A. So the total width of this hexagon is 2A, and the total height of the hexagon is the square root of 3 times A. And you can work through the geometry to figure that out. This is not very important here, but I just wanted to summarize it. These are the grading vectors associated with a hexagonal array. So here's our direct lattice. This is the thing that you would actually touch and see, and these are the lattice vectors. If we look at the reciprocal lattice, it's also hexagonal, and here now we have our grading vectors, or the lattice vectors of the reciprocal lattice, and here's what they look like. So that can be useful, although we're not really using it here and not completely necessary to use it, but it seemed like a good place to put that information. Last slide in this lecture. So we have a hexagonal array. We want to model it with the rectangular rigorous coupled wave analysis code. We need to identify some rectangle in this such that if we repeated it and stacked these rectangles together, we would reconstruct the hexagonal array. So what I'm showing on the left here is the hexagonal array, and here I've identified a rectangle, which we can call the unit cell. And here's a close-up of this rectangle and how the circles lie in there. But if we took this unit cell and stacked it next to itself, we would reconstruct a hexagonal array. Notice the width of the grid here is A. The height of the grid is A times the square root of 3, so about 50% larger or something like that. Now what this means is, if we choose 11 spatial harmonics in this short direction, in the longer direction, to keep an equivalent amount of resolution, we need more spatial harmonics. We might need 17 spatial harmonics in this direction. And that's where you take the hit in efficiency. If we develop really a hexagonal rigorous coupled wave analysis, we would only need 11 by 11 spatial harmonics, and we would line those up along the axes of the hexagon. Here we need 11 by 17 or 11 by 21, something like that. And so it hurts you in efficiency. However, if you're just running one quick simulation or just a handful, you don't have to bother with reformulating your rigorous coupled wave analysis code to handle that. Although I will say, if you ever did that, it's a little bit of a mind thing maybe to do that, but in the end you change very little of your code when you go from a rectangular RCWA to a generalized symmetry like hexagons. So the implementation is actually quite simple, but I wanted to point out here we can model hexagonal gratings even with a rectangular code, but there is a small hit in efficiency.